So this leads us then to what's called a chemical formula. And chemical formulas are great ways to represent how many atoms are inside a compound, usually, sometimes for elements, but usually for compounds. And there's different ways to represent these kind of formulas. But when you see a formula, there are some couple kind of rules you should follow. First of all, if there are any metals or cations in the formula, put them first. So for example, table salt is sodium chloride. Sodium is a metal, and chloride, the chlorine, is a nonmetal. So the metals always go first. It's never chloride sodium or something like that. If your compound has all nonmetals, which is very common, then carbon is almost always first and hydrogen is second, oxygen third, nitrogen fourth, these kind of things. It doesn't really matter after you get past CH and O, but those are usually how these things work out. So as an example here, I have some different examples here of a compound called methane. Now methane is CH4, so that means 1 carbon and 4 hydrogens, and that's how methane always is. Methane, by the way, is the main ingredient in natural gas. So if your home has natural gas for a fuel source or you use it for your hot water heater, CH4 is what you use. There's different ways to represent that CH4, and we'll talk about these more later. This is an example of what's called a structural formula. It shows how the atoms are connected, and you can see that carbon is kind of connected to all 4 hydrogens like that. This is a very common way to represent the formulas. Now, in future chapters in Chem 221, we're going to look at these big time. This is called a ball and stick model. Ball and sticks are kind of cool because it shows the geometry of the molecule. Like if you looked at structure B, it looks like it's flat, up, down, left, right kind of thing. This isn't flat at all. It's like a tetrahedron. Those angles are 109. We'll talk about all of that later. So there's a lot of importance for the ball and stick models, which are really cool. But the problem with ball and stick is that in reality, those atoms are a lot closer to each other than it actually looks. So the last one right there, that's called a space filling model. And that's actually probably the best way to represent it. These carbons and hydrogens, they kind of meld into each other, I guess, kind of like spongy stuff. And but the problem with ball and stick is you can't really see where the bonds are, so they're kind of awkward to use. But that is actually a better way to say it, or show it, I guess. So anyway, most of the time in our classes, we will use just this version right here, molecular formulas. They're great. They show the number of atoms, no problem. But sometimes, and we'll see this term, sometimes it's better to write them as structural formulas, like B right there. These ball and stick things are really, really cool in terms of geometry. We'll talk about that. But if you want to super get fancy, honestly, probably this last space filling model, D, is the best one. So these are just different ways to represent the different structures and molecules, formulas we're going to see in chemistry throughout this year. Here's another example. This is now with glycine. Now glycine has the formula C2H5NO2, and that's a great way to represent it because you see how many atoms are in there. There's 2 carbons, 5 hydrogens, etc., etc. However, that molecular formula doesn't have any information on the structure. So for example, if you look down here at my favorite ball and stick, the blue atom is nitrogen, and it's connected to 2 hydrogens, and then you've got this kind of black-gray carbon and another black-gray carbon. The first carbon has 2 hydrogens. The second carbon has an oxygen and also an oxygen-hydrogen group on there. So the structural formula has a little bit more information as to how the molecules put together, all right? And that's why sometimes you see molecules listed that way. Now, honestly, most of the time, the molecular formula is great, but there are some cool uses for structural formulas as well. Now, if you're curious why they're written this way, then the best way to break this down a little bit farther is into what's called a Lewis structure. And Lewis structures is something we're going to focus on in Chapter 4. A Lewis structure shows how the atoms are arranged and the different interactions. So you can see that one carbon-oxygen, there's 2 lines between it. That's a double bond. And the other carbon-oxygen is just a single line. That's a single bond. And we'll talk about how that all means. But again, the ball and stick will be better at showing showing the geometry. The Lewis structure is just 90 degrees and 180. The actual ball and stick shows the angles associated with it. And here's the space filling, which just gives me a headache to look at, but honestly, it is probably better. You can see the blue is at nitrogen connected to hydrogen, et cetera, et cetera. So they all have a use, just depends on what you're trying to do as a chemist at the time. 7 of the elements don't exist by themselves, all right? Most of the elements on the periodic table are just by themselves. So like helium, individual helium atoms. Lithium, individual lithium atoms. But there are what they call the 7 diatomics, which are really, really important. So I have this little silly expression here, have no fear of ice clear brew. And I recommend you check that out and memorize it because it's an acronym. It stands for hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. And those 7 elements don't usually come as individual atoms. They come to you as diatomics. So oxygen that we're breathing right now is O2. It's not just oxygen. And hydrogen is another example. It's H2. It's not hydrogen. So in the chapter 1 complete lecture, I showed an example of making water. It had hydrogen, little H2s, and oxygen O2s on the outside. Now you can see why. These 7 always come in pairs. Now, if you're in a super hot environment, like next to the sun, those H2s would probably break down to 2 H atoms. But by default, all 7 of these appear as a diatomic. Now, some classes, they will use what's called Hunkelbrief. Hunkelbrief is another way to know these 7 diatomics, but just kind of keep this in the back of your mind. These 7 are very useful. They're very common, and if you use just regular oxygen, you'll end up with a different result than if you use the actual diatomic oxygen. So pretty important. An allotrope is when you have more than one version of an element, and many elements have this: carbon, oxygen, phosphorus, and a couple other ones. Not all of them do, but a lot of them do. Carbon's really important. Carbon is the basis of life. All of our DNA and our sugars and caffeine, all those kind of things have carbon in them, and carbon has a lot of allotropes. Now, the most common allotropes of carbon, graphite, is what you might be using if you write down notes with a pencil, because pencil, quote unquote, lead is actually graphite. It's carbon. Sorry, it's not lead. Amazing. Anyway, graphite is basically sheets of different carbon atoms you can kind of see that are kind of stacked on top of each other. But you wouldn't want to try to write with diamond. So even though diamond is also carbon like graphite, diamond's one of the hardest substances known. So the diamond would rip through your paper and it wouldn't leave any marks on your paper at all. So diamond and graphite are both carbon atoms. It's just how they're arranged in space that makes the difference. And then around 1990 or so, scientists discovered what's called buckyball, or formerly known as Buckminster fullerene. And it's like a soccer ball of carbon atoms. It's a fantastic molecule. And there's a lot of interesting things that people are trying to do with buckyballs. I think we're going to hear more about Buckminster fullerene in the future. There's a few other allotropes of carbon too. It's really amazing how versatile carbon can be. Oxygen is another good example of an allotrope element. Oxygen O2 that we're breathing is super important, but you wouldn't dare breathe in ozone, which is O3. That's an allotrope of oxygen, another form that oxygen takes. Ozone would kill you. Not good. But anyway, ozone is important, keeping it in the earth. It keeps some of the radiation away and stuff like that. So it's just kind of cool. So an allotrope is just when you have an element and the element exists in more than one form.